So alright, welcome everybody to day 5. And last stream wasn't too bad. I didn't mind it. I think we actually got a little bit done. Hopefully these will follow suit, but I would also like to do a little bit of math. Maybe rant a bit about studying math and how it's presented, which I'm not a huge fan of in some regards. So as far as off-stream work goes, I haven't really done anything to the rig. I gotta hold true to that promise. Everything is gonna be on stream, but the shape of this controller is just driving me insane. So I changed that. I'm sure you guys know how to pull points around on a curve, so nobody will have missed anything fundamental for it. Nothing else has changed other than that I moved these. Before it was hidden, but it was centerward, so I moved that out of the way, but that's about it. So if you are reading something similar, you know, bit by bit in sync with the stream, you shouldn't be too far off. So the last stream yesterday, we basically worked on getting rotations working for an FK-like kind of model for the pedals, and we hooked up the wheel to the same, and we actually hooked up the very base transform for the wheel and all that. Now, if you've been following along, like maybe with simpler scenes or with something of your own, there's still a pretty massive, not really a bug, but there's a big gap in this rig, which is if you try to rotate, you will see everything rotating offset. It's even worse if you actually go off these axes. That's normal. It's just something we haven't got to, and I wanted to do vectors before doing that. So on a similar note, let me hide the stuff we're not gonna use, and actually let me also, so yeah, it's up. Let me also make these non-selectable, because yeah, it's driving me somewhat insane. And oops. All right, at least we only select the stuff we can work on. So cool. If anybody has any questions about the stream from yesterday, ask them now. I'll catch up with the chat for those super soon. In the meantime, I'm going to start adding a couple of things. And the stream delay to chat seems to be only about 5 or 6 seconds off, so that's not too bad. Now, what we started with here is we have the pedals have the local word input, so we're still staying true to what we said. We have edges between components, so the our God node, our master controls have an output edge, and we're connecting that directly to the input edge of the pedals, which is the local word for it. Then what we've done is that center word, we say, you know, maybe let's keep the underword, let's have these things or word space, so that for things that are all supposed to be, you know, the first tier of the hierarchy, it's easy to hook them up. Then we took the position of the actual output of the God node, just added the offset for with a simple vector addition node plus minus average, added the offset to where we wanted it to stand, and that basically drives the buffer. Now the other thing we're doing is basically taking the rotation directly from this. Now the rotation itself and the scale as well, but we're not scaling things. This will scale off center probably. This is also connected to something, so we'll have to scale these. Now the other thing is I have also swapped these two shapes, which were the wrong way around yesterday. Now that is actually what you would expect to happen, because what we're doing here is the rotation is linked 1-to-1, the scale is linked to 1-to-1, and that's correct. What is happening when something like this, when something like this is going on, it's not an issue with the rotation, it's an issue with the translation. Basically what we're doing is we're taking the position of this control, and we are straight up to the position of that point in space. We're straight up adding an offset in the form of another point, in the form of another vector, which is what we're actually going to get into today. Let's say we don't need the node editor, which is 5.1, and then we're piping that directly into the buffer for these things. So what is actually happening is order of operation kind of thing in a way, not quite, but let's reduce it to that for now. When you do these and you move the master around, the movement is fine. It's getting this vector, which represents this offset, added to it. But when you rotate, that rotation is transmitted directly to whatever is underneath or linked to it, whereas the position is still basically in word space. It's not getting, when this is rotated, the position is still being added word-wise. It's not being rotated together with the object. Now, there's easy ways to fix that, and there's good ways to fix it. You know, the straight and narrow is seldom the easier thing to do, but it's also usually the faster. So in the simplest possible scenario, what we could actually do is extend our input. So we know that we have, we know that we have a local word here that is going to be word space matched. And we know that we have something that is going to be at 5.1 off vertically that we want to follow that. There is absolutely nothing wrong if you don't want to, work on the maths part right away in just adding something to it and call it whatever you want. So let's say word to pedals offset. And we say it's an SRT. This remains an SRT. So what we will want to do is actually match this one to the buffer where we want to place things. And this is a super advanced features. If you're in 2016, you don't have it. Sorry. You could also just connect and disconnect. Now, what happens is we don't need this offset anymore. So we can now, and we have been true to the whole staying in word space thing. So we should be able to just go 1, 2, and 3. Ignore that. Wow, okay. What is that? Where has it shot my stuff into hyperspace? No, it's just whatever. So what we have now is basically the way a lot of people work, which is they build complex hierarchies of things to just inherit transforms. There's nothing inherently wrong with that, but when you start having components that have circularities and you want to address them, what am I doing here? Did I not? So that's a buffer. It's a local word. Am I not connecting something here? Ah, yes, of course, I'm not connecting. Okay, local word. This should get moved. I am doing something stupid here, am I not? I probably haven't connected a bunch of stuff. So that's correct. That's a pedal buffer. Huh. Okay. That's the bug there. So that's correct, that's correct. And, I'm stupid, sorry. Yep. I'm grabbing the local position, yeah. I'm grabbing the local position of the offset and pumping it in. That's no good. It's absolutely useless. What I want to do is the same we've done elsewhere and actually grab the word transform of it because the buffer is in word space and pump that in right away. I'm glad that didn't take too long to debug. It would have been pretty embarrassing. So, usual thing, word matrix 0, and then the reconnection dense. So now that should actually work. Yep. So we now have our proper word transform being multiplied correctly and all of that. Now the other interesting thing is that in this case, because of the way we've connected things, the rotation of the pedals is basically word bound, and that's okay. That's not necessarily a bad thing. We might want to keep that for now. Connecting local. Yeah, somebody was basically telling me there must be a fair bit of delay right now with the chat because somebody was telling me right now about something that in my word I fixed. So moving on, SVT buffer is taken care of. We don't need these anymore. Now it's getting hotter in here, so I'm actually gonna strip for the chat. It is now that kind of stream. I guess I'm a webcam rigger now. All right, back to it. So yeah, I guess achievement unlocked. First strip these on webcam. So moving on, vectors. When we work with positions, if we were to do something like this without actually having to add additional objects, and we'll get to an actual application that is more interesting when we look at an IK for the pedals. There's a couple things that you basically want to know. So let me get into a very short mini rant about what I think we're gonna do in this series. So when you need to learn about something like mathematics in general, what you usually encounter is that you are usually presented by academia, and that is true for a lot of resources online, even some of the friendlier ones, with a very vertical learning path. So let's say that you decide that you want to look at vectors, and you will find like 5 possible options about what you can learn, and you find that the one you want to learn about is actually part of linear algebra. And then you go, okay, cool, I'm gonna start learning about that. And right away, you're not even told what a vector is. First, you're introduced to linear systems, and you're not told exactly what a resolution system is. And then when you finally bump into vectors, you are immediately presented with another 500 options, like here's all the operations, which you might or might not have a use for. And here's proof of how each of these works, and then you have something that comes up pretty early on, like eigenvectors, which are supremely useful, but only much later on in your learning, and so on. Like this keeps repeating. Like if you try and learn about something like, and that is fine, because education in specific subjects tends to be very focused on what that specific subject is about. It's fine for academia. It's fine if you actually want to learn if you want to learn the abstract self discipline, be it some kind of mathematical discipline, computational, mix of the two. It's kind of tough when you actually want to learn just the basics of it, so that you can move on, you can apply, and you gain that more intimate and practical understanding of something, which makes learning the rest easy. So what I like is actually starting learning. Like I do like the first principles. I do think that the theory, like the raw theory of things, is important, is extremely important, in fact. And I don't believe in teaching just by examples without ever dealing with the abstracts. But at the same time, the actual learning paths that are usually proposed are pretty steep. And very soon you start encountering, if you're beginning at least, if you're an expert, if you're a PhD in maths, obviously this is not the case for you. But when you're starting, normally pretty soon you encounter some parallel discipline that you need to know something about. Like you want to start learning the basics of calculus, and almost instantly you encounter a number of other subjects that you need. So hopefully what we can do is actually introduce things in an absolutely minimal fashion as we go. All right, chat is still quiet, which is right. Now, so vectors are probably one of the most applicable things early on. They're also one of the easiest. Linear algebra in itself is also applicable and pretty easy to understand. So you are most likely already familiar with algebra, and algebraic operations, anyway, do not need to do that. Algebraic operations are some of the simplest you can imagine. So we work with real numbers, and we don't need to know much more other than they're basically the numbers that you're used to. They're 1, 2, and even the even fractional, so 3.6 and so on. And algebra works in those. And you have the classic operations that you're already aware about, most likely, plus and minus, addition and subtraction, and whatever, modulus. Modulo I think is actually part of standard algebraic. And division, whichever way you want to actually demarcate that. You have multiplication, which can be both the dot and the x, it depends. That actually matters. These are both multiplications, but in linear system they're different, and so on and on. And you are used to those working in just 2 terms, each of them being a number. You something like a plus b equals c. Now I hope that you know the basics of like linear algebra. If you don't know your additions and subtractions, the next part might be pretty steep learning curve because I'm not going to go over how you add numbers. So the idea of linear systems is resolution systems with a linear behavior, which is something that you don't really need to worry about, other than the fact that you can consider that like operating on sets of items that have some compatibility, and vectors are one of those things. So linear algebra takes linear systems and applies algebraic operations, and that's all it is. So if you have a number that is something like 5, that is unidimensional. So 5 is actually a point in time for something that is going down the sequence of real numbers. So you would have the classic thing that you see in graphs and so on. Now, if you couple that with another number, that's a classic Cartesian coupling, which probably mostly everybody has seen, I would imagine, when you say x and y. So you would have your x-axis down here, and then you would have your y-axis going up, and all you have is the coupling of two numbers. So instead of one number, you have two, and when you want to operate on them at the same time, that's basically, and you possibly want to operate on multiple couples of these numbers, that's basically you need a resolution system for that. They're considered linearly related. They can take algebraic operations, so that's linear algebra. So for something like that, what you get is, the classic drawings you probably did in even sooner than junior high, is like you get a point like that. Now, this is basically going to be a point that is defined by x and y. Congratulations, that's your first vector. That's a 2D vector. That's literally all it is. And the classic way people think of it, though it's, it can be a little bit misleading if you look at the absolute abstract of it, is it's pretty much an arrow pointing somewhere. And x and y, two-dimensional. Now, the 3D part of it is pretty much the same deal. It's except that you get to do it with 3 numbers. Okay, this is not super great, but you get the idea. So, let's see if we can make this work. Yeah, we can. So in 3D, what you basically have is to find this arrow that goes from one point to another, you actually need 3 coordinates. And again, that's all you have. So if you want the academic definition of a vector, it's basically something that has direction and magnitude. Now, there's a million applications, but the direction of something is literally the direction it's traveling in. It should be pretty self-explanatory. The magnitude is the length of that direction. Like Newtonian physics is the one where this is probably the most direct application you can find of anything, but geometry as well. And it literally means, move down this direction, that's the direction component of a vector, and move down that direction for, this long. So that's all a vector is. You will also find that you have things like quadrivectors, and that is where there's probably one bit that you want to take on axiomatically right now, as in just take my word for it, we'll deal with it. Because this is applicable in Maya. Now, in Maya, you will see that you have both a vector, which is actually a trivector, so it's got x, y, and z. And you also have, in Maya, they call it a point, which is not incorrect, which is a quadrivector, and it's x, y, z, and w. And this might be confusing. Now, there's a number of situations where you actually need this kind of stuff. But if you think about it, a direction and a magnitude like this, like we should be pretty satisfied with it to find the point in space. So I have my word space, which is the 0, which is where everything starts from, and I move in some direction for a certain amount of length. I should know the point I have actually reached. Now here's the thing, vectors can be used to describe two things. Sometimes they're used as direction-only vectors, and those are almost all of the time normalized or considered as if they're normal. So you don't look at the length property for something like that. If that doesn't make sense, we'll get to it. But basically, when you have your mesh in your 3D application and you have the normals pointing somewhere, that's a vector. And in the case of that vector, you really don't care about the displacement. You don't care that you're starting from this point and ending to this point at all. All you care about is that normal is facing in that direction. Whereas when you describe a point in space, so if this is your amazing mesh, and that needs to be relative to the word somewhere, each of those point positions compared to some hypothetical word is a displacement vector. So it's a vector that basically tells this point where it actually belongs in that 3D space. Now, when you need to make a distinction between those two types of vectors, using quadrivectors is one of the most common things. There's set of benefits to it. They align with vector operations on CPUs and so on, but we're not going to go into that for quite a while. So that's where the W comes in, and that's the factor. So when you have a vector that is a trivector and you just want to use it to express direction, like for the normals, normally the W factor is implied, and it's implied to be 0. When you have a point and you want it to be displacement, if you're using a trivector, the W factor is implied to be 1. So the difference between something that just has direction and something that is displacement is the W factor. But the more interesting thing, I guess, if you ever have to deal with it directly, is that as you have a vector that goes like this, what that W factor really is, and it can be something other than 0 and 1 actually, is basically the direction of something is how far is in what direction you want to travel, and that's determined by these pre-numbers. The length of the vector, which is also determined by these pre-numbers, basically expresses the potential of the vector. So this vector has the potential to displace from the word space all the way up to here. Then how far you actually want to travel down that vector is actually the W. So if you express a W of 0, you know you're going in that direction. You know possibly that the potential is that one, so you likely don't care if you're using a W of 0. But you don't want to travel down that, which is pretty much what normals do. Whereas if you want to travel the full length, or even more if you upscale the W past the 1 point, then you might have some fraction of W in here expressing how far down the potential of that vector you want to travel, up to the point where at 1 you reach the full displacement that the vector was describing. Now, if the chat wants to catch up, this might be a lot of theory all at once, and a lot of it you kind of have to take on faith. This is kind of where we're starting from. If something doesn't make sense, please tell me. If you think this is useful, also tell me. But anyway, let's move on. Most of the time, and one of the reasons I'm mentioning this, is that in Maya there's a very big difference between an actual float vector, which is usually just this, and a point. So I've seen people like writing notes and stuff like that and getting stuff that just doesn't move in space, and they're wondering what they're doing wrong, and all they were doing wrong is that they were using a vector and not a point. So they basically had no W factor. The W factor was assumed to be 0, and their stuff was just not moving. They were doing everything right, but those displacement vectors were never told, go and reach your full potential of displacement. So this is pretty much all vectors are. Now, vectors and matrices, like vectors are basically matrices that have just one column or one row. We're not gonna do matrices yet, but the way you're gonna see them written is often something like this. So this will be a 0 vector that has and it's a quadrivector that is is pretty much left at word or whatever your reference frame is. So, and if you don't know what a reference frame is, it basically says, there's something that I need to refer to, which is usually your word space or might be something else. That's it. So you're always expressing displacement or direction and stuff like that compared to some reference frame. And this is how you will often see them written, and this is basically a column vector. Come on. Okay. And then the other way you'll see them written is something like this, and usually these are comma separated, but you can find different ways of expressing them. And this is a row vector. There is literally no difference whatsoever. This is a matter of convention. When you get to matrices, there is actually a pretty big difference, and whether you choose column matrices or row matrices does affect things, but again, that's for a while down the line. Now, next thing we want to do is, so if you have two vectors, we want to operate on them in an algebraic fashion. And I hope I can actually clear a fair chunk of these in the next 50 minutes or so that we actually get to apply it. If you take two vectors, whatever they are, and not super, let's use trivectors for now. Let's assume that the W is 1 that we're using displacement vectors. There's a bunch of operations you can run on these. So the first and simplest is actually piecewise. They're piecewise operations, and most of the algebraic operations that make sense, addition, subtraction, division, and multiplication. That's kind of I don't remember the symbol for the piecewise multiplication, but it's not the dot. They will apply to these. So, and here's the interesting bit. Well, not the interesting bit, but here's a pretty important bit. Each of these parts of a vector, each of these numbers, that's considered a scalar. So a scalar isn't necessarily a float or anything, but the discrete part of a piece of a system in linear algebra is a scalar usually. And take it with a grain of salt. You can go and do a bit more reading on it if you want, but that's enough for us to start explaining things. So most of these operations piecewise are pretty simple. So if you want to add two vectors, and these are your two vectors, what you will get is actually that your final vector, and for the record, I think Maya is pretty much entirely row based. So it will be 1 plus 2, 2 plus 3, and 2.5 plus 1.5. So your resulting vector will be something like this. Now, and that is actually pretty useful when you want to add positions in space, in example. So let me make a case for that, which is if in Maya you have an object that is, you have your word space somewhere, and I'm not going to start switching colors all the time, but at least some differences. So you have a position in space. There's an object that is positioned somewhere. This is the first item in your hierarchy. Let's call it A. And you have a hierarchy that is structured something like this. Now, in the case of A, which is going to be under the word, the local transform, which is when you look at the translate, that's basically that vector. That's x, y, and z. That's what we've been talking about insofar all the time. And that is local to its reference frame. In this case, it's the first one. It's under the word root, which is pretty well hidden in Maya. Tricks to get it, but you don't want to. And that's its position in space. Then if there is an object that is under B, and that is that has a translate property, which is going to be tx, ty, tz usually, then that is expressed locally. So if your object B is here, what it's actually expressing there with this position is this vector, basically. This one. It is not at any point giving you this one. You don't have it. Now, if you wanted to find that, if you wanted to find the word space position of B, what you would, and all you had was the local transforms, and this is actually what happens in lattice systems. What you would have to do is basically take A and B and take, their t vectors and add the map. So let's say that we have TA and TB. You add the map, and what you get when you add vectors, which is piecewise addition, is literally just that, is the vector that's gonna be going from the starting point to the end point of the last vector. So there's no such thing as a squiggly vector that goes around at an angle like that, but if you want to find the final point that you get into, that's it. So that's when you use addition. Now, again, I'm relying on the chat to tell me if something doesn't make sense or anything like that. Apparently my own video preview is buffering right now. I hope this isn't dropping. Let me ask chat. Anyway, so the subtraction is also pretty interesting actually. So if you have the word space, so far no buffering for me, it's okay. The stream isn't broken, it seems in good health. It might just be something on my end for the video preview. The subtraction is actually pretty interesting. So if for some reason I have the word space of B, which means, again, not too many colors, but some, otherwise this becomes completely incomprehensible. If you have the word position of B, and that's going to place you somewhere here, and you know, it might be these 3 coordinates, and that B is actually under A, and that A also has a word position, and we know it to be here, whatever those are. Now, if you subtract 2 vectors, it's basically going to give you the displacement that is required to go from one vector to the other. And again, it's a piecewise operation, so for a subtraction, you do the same you did here, algebraic operation. Now, the direction that you subtract things in is actually pretty important. That's also the same way that algebraic operations do work. So if you do something like 5 minus 3 in normal, you know, scalar algebra, what you get is going to be that you're going down 5, which is literally just progressing down a line, and then you're going back 3, so you end up at 2. Now, if you extend that line to have a negative reflection, and you were to invert the order of these, what you will get from 3 minus 5 is that you will basically be going up 3 and then going back 5, you end up at minus 2. So, and this is often, you know, this is non-commutativity, so the order of the operands in an operation actually matters. But the interesting thing about this, in a way, is that what you, and especially if you have more than 2, then it becomes a little bit more complicated. But the interesting thing is that when you have 2 operands in a case like this, it's a perfectly symmetrical operation. Now, vectors do reflect that. So if you do, in this case, let's say that this is B and this is A. If you do B minus A, play with it, but the second term is basically where you start. So it will get you that direction. If you were to do A minus B, you will still get the same magnitude and the same, let's say, general direction, but it will be traveling in the opposite. So it's actually a different direction, but hopefully you get what I mean. So you would actually be going in that direction. That's pretty much it. So the useful thing about it is that if you have the word position of 2 items, and that is often the case if you're placing thing in the word because you're doing a broken hierarchy or a flat hierarchy or whatever you want to call it. If you're dividing things, so you're not relying on the hierarchy in the C and DAG to actually move things around, you get a lot of word positions and very few relevant local positions. But sometimes you actually do have A and B, and they're both word, and you want to know what the actual displacement from one to the other, as if they were related, you know, parent-children relationship in the DAG, will be, and that's a straight-up subtraction. Now, another interesting property is going to be the piecewise multiplication, which is pretty easy to do. So let's say that you have a vector and you want to multiply it by a single scalar. It's not a scalar multiplication, I'm confusing with that, we'll get to it. So you have x, y, and z, and you want to multiply it by you want to multiply it by just one scalar, or you could actually piecewise multiply by another vector. So multiplying it by one scalar is the same of multiplying piecewise for that scalar by repeated for x, y, and z. What you get is pretty much a vector scale. So if this is your vector and it was of length 1, which is a normal vector, and that's the next thing we're going to discuss as soon as we're done with this, and you multiply piecewise by a scalar that is 2, and I really don't remember what the sign is. It might be something with the absolute in or something like that. But you get the idea. Then what you get is a vector that is twice the length that it was before. So your vector remains the same direction, just its magnitude is increased. If this wasn't 2, if this was 0, 5, then what you will get is a vector that is half the length of what you had before, but the direction the direction remains unchanged. Now this is also pretty important. So what happens when you have a w factor and you look at multiplying that w by the potential of the vector is pretty much this. That w is multiplying the potential of the vector. So moving on, dot product and cross product, not quite gonna get too much into it, but it's good to know that they exist. So there's two ways that you can multiply. And by the way, sorry, a quick note, the division doesn't, quite exist. It's the same as a multiplication because dividing 1 by 2 is actually the same as multiplying 1 by 1 divided by 2, so it's the same as doing that. So the multiplication actually covers division cases. That's true for a lot of algebra as well, and it's actually good practice in performance-oriented programming. With that out of the way, now if you have two vectors, there's two ways to multiply them. So without talking about this piecewise thing, if I have two vectors, there's two multiplication operations. One is the dot, and it's also called the scalar product, because despite the fact that these are both x, y, and z, and this is where you can actually go on Wikipedia. Now that you know that you're down to a narrow enough piece of knowledge that you want to deepen, it's pretty easy to find something that's applicable. So the dot product will basically multiply and add the various components, and it gets a single scalar, and that's why it's called the scalar product. So, and it actually has some very interesting properties, because if the receiving vector is normal, then basically that dot product is going to be the length of the one vector projected onto the other. So let's actually get, so if I had something like this, and I happen to do the dot product between, and this is length 1, the dot product is actually going to give me the projection of this vector on the other, and well, it's going to give me the magnitude of the projection of this to the other. So if I wanted to project A over B, and B is actually normal, I could get the dot product, which will give me, really? Okay. Sorry, my tablet started arguing with me. So what I could actually do is basically get this length through the dot product, which is the relationship between the two vectors. It's valid even if this is not one, but then you start getting skewed projections. Then take B as a normal multiplied by this, which is an L, better have a serif on it, and you basically get this vector. And you could do it the other way as well. Now there's interesting properties to these, because if you do have vectors that are like that, and that is the classic case where you go meshes and cameras and so on, the scalar product, the dot product, is actually signed. So my result in this case will be minus L if the vector was reflected. Which tells me that the two directors are facing away from each other. So that's an interesting property. When it comes into play and it becomes useful is if you have a mesh and you have a camera, well, there's a million cases where you actually use it. But if you have a camera array and you're looking at a mesh and your mesh is like this, and you use slightly more complex things when you do these kind of operations, but they all start from this. So you have normals like that. If you take the camera array and for each point you compare it with the normal of the point, you will see that this normal, this ray is going this way, this normal is actually going to be negatively projected. This normal here is going to be negatively projected. And you can see, we don't care about the difference between these, we just care about the direction. This is also going to be negatively projected. So any normal that is negatively projected on the camera array is going to be facing towards the camera. So chances are it's on a point, that it's on a polygon that we're interested in. Now, suddenly, if we get to a polygon that has the normals pointing this way, and you do the dot product with the camera ray, let's copy that ray here for a moment, your dot product in this case is actually going to be positive, which means you know that the normals are facing in the same direction that the camera ray is, which means chances are that this polygon isn't interesting. I can actually cull it. I can remove it from computation. So that's when you use the scalar product. Ooh, one example. You actually use it for a million useful things. So hopefully that still makes sense. Now, orthogonality is the next concept, which is trivially easy. You have an angle, And the angle, well, you actually don't need arrows for something like that. If you have a circle and you're pretty much, oh come on, I can do it. No, apparently I can't do it. So imagine this is a great circle. If you basically move down the circumference of a unit circle, which is a circle of radius 1, the angle is the slice of pie that you're cutting as you move down that way. That's radians, which have a nice relationship with circumference and radius and so on. That's all it is. That's all the angle is. So with that, if you imagine these as arrows, you know, they will be pretty close to vectors. Whenever the angle between two of these, when the precurrence is half pi, so you've gone down a quarter of a circle, or 90 degrees if you use those degrees, that is a rectangle. So that's pretty much it. And now when items are at a rectangle, they are orthogonal. And this is still holding true even in 3D. Like in 2D, it's pretty easy to imagine. You just go down that way, you know, you hit 90, half pi, whatever you want to call it. Congratulations, it's now rectangle. And that is also interesting here, because when the dot product of two vectors is 0, it's because when you think of projecting these on the other, again, the dot product is not a vector projection, it's used in one, but it's a useful key to think this in. The length of the relationship between the two, the length of the projection of one and the other, is going to be 0. So if the dot product gives you 0 for valid vectors, assuming they're not 0 vectors, you know that the two vectors you've just looked at are actually orthogonal. Now, the second multiplication we want to look at is the cross product. Now, the dot product is called a scalar product because it gives us one number. The cross product is called the cross product because it actually runs across all three parts of the vector. It's also called the vector product because it gives you a vector. So I'm not going to spend hours on this. If you want to look at the actual numerical operations between the two, you can just, you know, pick them up on Wikipedia real quick. But what happens in a cross product is that basically you're going to be doing something somewhat similar to a dot product. So you're going to do a scalar product, but across for each of these terms. So that what you get is, you know, three operations are going to get you your x, and three operations are going to get you your y, and another three operations are going to get you your z. So that's why it's called a cross product, and that's why it's called a vector product, because it's a multiplication, but multiplication plus addition if you look at the algebraic parts, but it actually gets you a full vector. It gets you a trivector, or whatever the actual dimensionality of your vectors is. Now, the interesting property of that is that if you have two valid vectors of any kind, and valid in this case is non-zero, what the dot product, the cross product actually gets you is a vector that is normal to both of them. So if you look at the word matrix, the classic word matrix of most of the transforms that you deal with in Maya, and think of it as, let's actually point it out. If you look at something like that, if you look at these, a matrix is, to oversimplify, is basically three vectors. It's three arrows pointing down z, pointing down x, and pointing down y. So as you express orientation and stuff like that, orientation and scaling in this case for a 3x3 matrix, it literally is those three arrows. Each row, because matrix is, Maya is row matrices, is one of those arrows. It's three vectors. And this is called an orthonormal matrix because assuming there's no scaling, because all three axes are normal, which is what we're going to get to next, and they're all orthogonal to each other. They're all at 90 degrees from each other. So what is pretty useful, and you know, hopefully we'll do some applied, is you have two vectors, and I could have drawn them in a slightly better configuration than these, I guess. It's kind of tough to express 3D while drawing 2D scheduling real quick. But if you cross product those two in example, what you will get, so if you had two vectors like that, what you will get is a vector that is normal to both, which is actually interesting for a million different things. Now, the cross product is also non-commutative, so the order of operations actually matters. If you do something like A cross product B, and you just have to try it, it depends on left-handed or right-handed matrices, not going to go in that just yet, you will get this vector, it goes in that direction. If you actually do B cross A, you will get that going in the other direction. So, hopefully these two make sense. If the chat wants to let me know if I need to slow down or go over something else, I can. Until then, let's move on to the last thing I actually wanted to get in, which is the length of a vector. And we've been doing all of these. I wanted to do one of the streams on maths because I said, you know, math, easy, approachable maths from first principles is one of the things I would have done. And B, because I want these to be done before we get on with the rest. So we say that a vector has a magnitude, which is its length. Now, if that length is 1, and you need a serif, for those that don't know typography, when you, like, if you write an L like that, that's without a serif, so sans serif, and if you write it like that, that's a serif. And if that length is exactly 1, that is a normal vector. The normalcy of something, in this case, is assumed to be 1. That's pretty much it. That's when you hear the normals, it's just because they're all vectors of length 1. Now, at length 1, the vector has a ton of interesting properties. So that is why they're so important. It makes projection, like it makes using the dot product viable to do non-skew projections, and it does quite a few nice things. So the next reason why we're interested in this is that because you can actually normalize a vector. So let's say that I can do this. I have a vector of some length, and that length might be, you know, 4.5, and I want to explicitly put something down this vector at 2.5 units. So you can always do the ratio between those and actually get the number out. But the basic principle of it is if you take this vector and you normalize it, and it becomes, well, that's not quite at scale, but so what would it be? This is entirely not at scale. We don't care. We're rebels like that. So if this is actually of normal length, then you can multiply by 2.5 and you will get your vectors like that. Now, this is, normally you would actually take the length of the vectors and find the ratio between the two and piecewise multiply the vector you're interested in and by that. But a lot of nodes, a lot of stuff you find around doesn't quite give you the straight up option. So very often you find that to get a vector at a certain scale, you want to normalize that vector and then multiply by a factor. And what this is based on, which I'm not going to spend a lot of time on, but just to mention it, is Pythagoras Theorem, which hopefully everybody remembers from school. But if you don't, he was the guy that figured out that if you build a square on these sides of a rectangle triangle, I could have drawn a smaller triangle and this would have been a lot easier. Now, if you build those two squares and you actually add up their surface, so let's say that this is, yeah, sure, let's keep using A and B, this is not confusing at all. So if you add the surface of A and B, which is probably gonna get you, you know, something like that. Now, this square, that is the addition of the two, just happens to be the square that is built on the hypotenuse, which is the long side of a rectangle triangle. Now, if you use square roots, so squares and square roots, if you have the length of these, you will go let's say that the length of A is lowercase a and the length of B is lowercase b. You will go a squared, which gets you the surface, plus b squared, which is the length of these. It gets us these two surfaces, you add them, and then you do a square root. We haven't done exponentiation. I'm not going to, because I actually want to show a couple things in Maya for the application of these. But look up square roots, they're pretty easy. So this is Pythagoras Theorem. And when you think about it, this actually happens to work in multiple dimensionalities. So that is literally how you find the length of vector. When you have a vector in 2D, let's change color just for the sake of it. When you have a vector in 2D like this, the x and y coordinates of that vector are, if you think about it, pretty much, this is how far we've gone down the x, this is how far we've gone down the y. They are the two sides of a rectangle triangle. So if you take a vector that has x and y and you do x squared plus y squared, you find z squared. Well, sorry, you don't find z squared at all. You find the length of this vector, the length of this side, so the length of the vector itself, which will be, what is it, the length of, is it that? Anyway, the length of v squared. So that's pretty much it. It works in 3D as well. So if you add one dimensionality, it's like building, you know, triangles of triangles kind of scenario. And so it still applies. If you do the square of one plus the square of the other, you find this one. Then you add the square of your third coordinate, which happens, you know, one is the square of this and the square of that one, and the other is the square of that. It keeps working basically. So if you go down dimensionality and you keep squaring each coordinate, it works out. The W factor doesn't work like that when you use a quadrivector that distinguishes between normals and displacement, because it's a factor, it's appended at the end, it's not one of the three coordinates. It works only for coordinate systems. So, all right, that was took longer than I expected. I was hoping for half an hour. It took me 50 minutes, but we get to apply. Now, in 2017, I don't know if it's in 2016, you can find free nodes that kind of do the same. You can use expressions, but in 2017, they finally added vector operations that make sense. And before there were fewer, I think so at least, but somebody might correct me. So you finally have a node. Come on. What can... Is it really crashing now? Nah. I must have done something. Okay. So I'm in this weird plus mode and I don't know why. I don't know what I've done to deserve this. If it's my keyboard playing up or something. Come on. All right. It's always interesting when this happens. So yeah, I suspect Maya is crapping the bed right now, or my PC is. So can you guys still hear me? Can you peep up in chat and tell me if it's still streaming, if you can still hear me? Only in live stream. Yeah. It's I don't know what is going on. Something seems to have taken over my keyboard. I don't know if I'm in some evil shortcut of doom kind of mode, but okay, how to solve this? Yeah, this is bizarre. Okay, how do I get out of this? So something is seriously messed up with my system right now. I can't right click stuff. This is horrible. I might have to close the stream early unless I can close it and restart it. Or I could disconnect and reconnect my mouse, I guess, but all my clicks have been stolen from me. Yeah. Alright. So all I can do is actually tab between windows and use keyboard shortcuts. See, it's okay. Do I want to save these? So let's see if I can save it as a separate item. It seems that Maya is the one that's at fault here, to be honest. Okay. Wow. I have never had this happen to me before. Yeah. What do I have no idea how that happened. But Maya was happily taking over my keyboard, or maybe Mischief is, who knows. Yeah, sure. No, something else is. Anyway, all right, I gotta call it because this is getting silly. I can answer questions though. I mean, we did make it the hour. I was hoping to actually do some applied of it, but clearly fate disagrees. When in that, blame Maya. No, well, apparently it's not Maya. I blame Maya too quick on that. So, but I have no idea what is going on. I was super interested in the practical Maya side. Yeah, I wish I could get to it, but I mean, it's getting sort of late, and I would have to probably kill all my applications, which includes OBS. Something with like. See, I can't. If I could click around, I could at least try and kill a few things. Let me see. I really wanted to show that actually. Can I actually kill manually some of this stuff? So I'm actually murdering a lot of services here. And it's still not making enough of a difference. Yeah, all right. I can't do anything other than take questions, I guess. This is very bizarre. Yeah, no amount of stuff I close or services I shut down makes any difference. So I was super interested. Okay, Maya 2016 has the vector product node. Which nodes did you say they added in 2017 to make things easier? So the product node has been there for a while, and it's that I remember. It's always said dot product for sure, and it has an option to normalize, which is super useful. And but I don't remember that having the cross product before 2017. It might be 2016 or 2016.5. Before then, I certainly remember it being really, really crappy. So, yeah, just you can find a ton of like free math nodes out there if you before we actually get to write our own. If you really want to experiment with dot and cross product, which I will recommend doing. So, any other questions that I don't need Maya or Mischief for? Pretty sure 2016 had the cross product operation. Yeah, it's possible. Okay, it's honestly those are nodes that I started writing because I really needed them like ages ago, and I've always ended up writing them or using my own. Then whenever I roll back to vanilla Maya for one reason or another, which is probably a few days once every 5 years, I find that they added something useful. What are some other use cases you use the dot and cross for like the camera culling? So there's a ton of uses, but when we'll get to transforms, when we'll get to matrices, that will make a lot more sense. But here's the thing: if you have a ground plane, in example, so it's just one of your axes. The ground plane can be defined by its normal axis. So in this case, it will be the y, and I have to use the, my fingers in the webcam because I don't have Meyer mischief. Any item that in your word space is positioned anywhere, if you take that and you dot product it to that axis, you will basically find where it sits in height. Now that is basically it's going to be its y component. So you could just take the y component of it. Now, however, it's more interesting when you look at vectors that are maybe non-normal or pointed somewhere else. So when you want to find where one vector sits in relationship to another, so if you have an object that's oriented that way and you want to project some other object in space down its y, you could transform this vector in that matrix ops. We'll look at it, but matrix ops are pretty expensive and it will be overkill in this case. Or you could take the axis of that object, take the vector of your other object in relationship to it. So you subtract first, you find one object in relationship to the other, then you run a dot product, and it will pretty much tell you, okay, I am this far up and down the y-axis of this other object. So whenever you do things like pistons and stuff like that, it's super useful. Whenever you want to project from any object to any other object, it's super useful. It's even more useful when you look at it in conjunction with trig, which is what I wanted to actually show. But by running things like dot products, you can find some angular coefficient. And I keep mentioning it as a projection because it's very easy to visualize, but it's not. It's a lot closer to the angular coefficient or something. It's very useful to find the direction of something in respect to something else. And the cross product is pretty neat when, well, again, there's a million cases for these things, but if you have any two objects and you want to orient a third object by those, the classic up vector for two objects that point that way, you want some ideal up vector and you don't want it to be explicit unless those two overlap or face 180 away from each other. If you get the cross product between the two, you always have a pretty good up vector for going between those two objects. So those are some of the classic applications. We'll actually see quite a few of them eventually. Doing it with my fingers and the pen is like pretty embarrassing, but hopefully you get the idea. So what shortcomings do the vanilla Maya math nodes have? Look, if you want a generic node, none. It's fine. Use them. I like atomic nodes. I like nodes that only do one thing. There's performance reasons, but they're on the edge of being absolutely relevant, to be honest, when you look at the grand scheme of things. Any node that needs to run a number of operations based on an enum will always cost a little bit more than a node that only runs one type of operation. That difference is usually going to be negligible, so that is not a strong argument to make. The only argument I can make for it is they used not to have any useful nodes. I used to write my own, so I've always had them around. They only take a few hours to write, like dozens of the useful stuff. And I like the fact that you get a node that does the cross product and not one of 5 things, so that when I look at my graph, I know at a glance what I'm doing. They're not strong arguments. I mean, there's a stronger argument if you want to distribute what you do for using the vanilla Maya nodes for as long as you can, unless they're absolutely horrible at something. So, all right, I don't know if this is still going. I mean, Twitch is definitely freaking out a bit. It's telling me my video preview is horrible. I don't know if I am actually online with these. Yeah, possibly not. I will definitely need to kill all of this stuff. I can still hear C, still no problems. Okay, that's good. It must be, I don't know. I really don't know what it is. I really have no idea what is doing that. Everything seems to be working fine, except it catches. Just my click events are gone, except for something, unless they're on the desktop. That is so bizarre. Right click on the desktop works. That's anyway. Yeah, keyboard gremlin will not silence the code. Yeah, I wish, man. Now this is where Can I? Yes, I can actually use the shortcuts for OBS. That's great. So, all right. I mean, this is enough of my promotional desktop background, I guess. I'm sorry. I was hoping to do hour and a half, and was hoping to actually. I finally got to the end of the theory, and I could actually show it in Maya. But apparently, you know, the gods are not willing it. Might do a quick stream during the week and catch up to these, maybe 45 minutes just for the practical applications. So, all right. Thanks everybody for watching and making it through all the blackboarding. It was a lot of it, but it's the kind of stuff that if we actually make it to proper seasons, you know, once every few days there will be something like this. It's stuff that I think is important. It's stuff that I like to do. Feedback is appreciated. If it's something that you want to see more of, less of, and stuff like that. If you're watching these on YouTube and you made it this far, you know, leave something in the comments like whether you like or not, or you know, you want it to be scarce or not. All right, and thanks everybody. I'm gonna shut these down. Have a good rest of the weekend, y'all.